I'm going to be futzing on my computer for just a minute, because I'm moving a little bit slow this morning. So joining me today is the lovely Emma.
It's only for you. It's early for you. It's late for me. I understand.
And I've just had a little bit of a struggle this morning with getting up and going. All right. We look like we are live on all the platforms. Fantastic. Still don't know why I can't see my Twitch chat. Welcome to, I'm just looking at a random figure. This is what the paper is. Utterance-level dialogue understanding, an empirical study by all of these authors. And something that I have not actually told Emma, surprise, is that Soujanya DM'd me on Twitter and let me know his list of the sections of the paper that were the most important. So I thought today we could go through and make sure we hit all of those. And I'm still trying to get my chat up.
Oh wow! So one of the writers actually contacted you. That's nice.
Yeah, it's for folks that haven't spent much time in research areas, as long as they're not super busy all the time. A lot of researchers, if you reach out to them and have questions about research in their papers, will generally be happy to talk to. Gregory Hinton, who is one of the founders of the idea of deep learning, probably not going to have a lot of extra time. He might respond, but researchers who are working on something that's a little bit more narrow will often have time to just chat.
Yeah, engage.
Exactly.
Engage on the paper. Cool.
All right. So the important parts of this paper are label transitions in section 4.1, which I believe we read. Just a quick overview of what we did last week, because I need the refresher. We talked about this model that they're using of conversation. So at every turn, what a person says is influenced by what the person said to them last turn, what they said that made that person respond, or what they intended, because a speaker has access to their intentions in addition to just the utterance. Their intent this turn, their emotional state, the topic they're talking about. I don't remember what P is, and I don't remember what S is, but basically all these factors come together when they're deciding what to say next. And then we talked about sort of how emotion plays into that. And then we looked at a bunch of discussions of how conversations in these different data sets tend to go. And these are the data sets that we did not read about in any great detail. Scroll. Section 4.1. Okay, so one section that we did read was this one that looks at sort of the patterns in conversations in these data sets. And we found, yeah, it was.
Yeah, it was interesting to see how conversation would go back and forth and what would be coming up the most, actually, or what would be most present. And I guess you can kind of gather a lot of information from that as well. If it started with no emotion, it would tend to also go with further no emotion and back and forth like that. Yeah, it's really interesting.
It was, and that would be I think very relevant for people who are writing responses. If you know that someone's frustrated, you can you probably don't want to be frustrated back at them, but you could be neutral, or you could be conciliating. So I believe these are humans, human dyads. And this figures people tend to mirror emotions in this data set, but not necessarily this data set. This data set is a lot less emotional overall. And then people don't tend to mirror persuasive strategies. So like if I'm trying to get you to donate to my charity, you're not going to be like, no, you should donate to my charity in response. Anyway, probably it happens sometimes.
Maybe,
okay,
yeah.
So section 4.1 and then section 5.1, which I don't think we read. Let's see.
Yeah, I remember we stopped shortly after that, I think.
Yeah. MiniBatch. So we talked about this a little bit. So when you're training a model, you send through a bunch of data, you get back the prediction from the model, and then you use that prediction and you're like, the set of predictions, and you're like, okay, these ones were right, these ones were wrong. The right ones keep going in that direction, the wrong ones try a new tactic or shift a little bit. And the idea with MiniBatch is you take like small sections of data, pass it through, update, as opposed to putting all the training data through, updating all the training data, etc. So the theory is it should train a little bit faster. So do you want to start with this section, and
Sure.
we can talk about things as they come up?
Yeah, definitely. So MiniBatch formation technique. So to understand the sensitivity of the training to utterance distribution across mini-batches, we consider two scenarios. So it's also in figure 10. Dialogue distribution across mini-batches and utterance distribution across mini-batches. The first scenario keeps... do you want to jump in? Or...
Yeah, I'm trying to imagine what that is. I think we're going to talk about it.
You mean the difference?
Because this almost sounds like...
The same.
Oh, sorry, go ahead. Oh, I was going to say, the second one almost sounds like they're just like randomly sampling utterances from various dialogues and just like passing them through randomly.
Yeah.
And then this one is they're picking like chunks of dialogue and then passing it through.
Oh, okay. That's interesting. Yeah.
Would be my guess.
Maybe we find out too. Let's see. So the first scenario keeps all the constituent utterances of a dialogue in a single mini-batch. Allows classifying them using a single RNN. Pass with O, N, cost, and N is the number of utterances in the dialogue. This is the default mode of operation for the BCA LSTM and the dialogue RNN. In contrast, the second scenario may distribute the target utterances to be classified across different mini-batches. This leads to one RNN pass per utterance that is considerably computationally costlier than the previous scenario, which is O(n)².
So if you have 5 utterances, it's going to take, and it takes 5 seconds. With this mini batch, it'll take 25 seconds. Or if you had 100 utterances, it would take 100 with this one, and then 100 squared. 10,000 seconds with that one. So this approach is going to scale better. And that is keeping the chunks of dialogue together as opposed to randomly sampling turns from the dialogue.
Cool. So yeah, this leads to one RNN pass per utterance that is considerably computationally cost. Oh, sorry, did I say that? Yeah, I did. Further, the representation of a particular context utterance is very likely to vary based on the mini-batch due to the update of network parameters by a fraction of their gradients per mini-batch. This curtails joint training of all the constituent utterances in the dialogue, precipitating poorer performance as evidenced by figure 11. So we found that when the batch size is small, baselines with dialogue level mini-batch perform better than their counterparts with utterance level mini-batch configurations. However, the difference gradually reduces with the increase in the batch size. In fact, in several datasets, as shown in figure 11, which is the batch size equal to or greater than the 16, the performance difference between these two different configurations are not significant.
Okay. So this is 11? Yeah. Oh, I see. No, I don't. Performance. Presumably this is on a scale of 0 to 100, so it's like percent correct or something. Accuracy. And okay, so the circles are the dialogue-based batch, where you keep the dialogue together. And then these little, I guess those are X's? Crosses, I guess, if you're being British about it, are the ones where you're just randomly sampling from the utterances. And what they're saying is when you keep bits of the dialogue together, you get better performance faster. So we should see the circle lines going up quicker. And it looks like that is the case for this daily dialogue.
Higher percentage means higher accuracy, is it?
Yeah.
Okay.
I don't know like specifically what they're doing, but I think it depends on the data set. So my guess would be that here, okay, yeah, so this is emotion detection, intent detection, whatever ER and EE are, and then dialogue act. So like persuade, deny, agree, that sort of thing. And it looks like, so for sure for this one, we have like the circles always above the X, the circles above the X until you get to a bigger batch size. So adding more data every pass. And that's sort of the general pattern. So I guess the recommendation would be, if you're using smaller batches, you should sample little chunks of your dialogue rather than randomly picking utterances.
A good general, good way to do it.
Which I think, I don't know, especially if you're modeling things that have a transitional probability, makes sense, because point X is going to be dependent on point X minus 1, X minus 2, blah, 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 back into the past. So if you're keeping those together, you should get more information, is my understanding.
And what do you think out of all those performs the best, generally, you'd say?
So it does look like this bidirectional, I forget what C stands for, LSTM is doing better than the glove CNN. Overall. Yeah. It's hard to compare between data sets, though.
Yeah.
Especially because these are also different tests.
Yeah, different, like you said, we're trying, also trying to, I guess, try to keep data sets as similar as possible, but these are quite different, aren't they? It's kind of hard to compare.
Which, that can be useful for things where you want a general principle that'll work in a lot of situations. And I will say that sort of general principle that the dialogue batches seems to do better does seem to hold across a lot of these data sets. But yeah, it is a little bit unusual for...
So BC LSTM holds its own pretty well.
Yeah, definitely. Yeah. And that would be as opposed to like a transformer model, which would be sort of the newer architecture. All right, I'm going to take the next section. When comparing two models tasked for utterance classification in dialogues. Okay, so all of these are sorting each turn into a group. The mini-batch construction process should be paid careful attention. As we have explained above, the batch size is a crucial hyperparameter when juxtaposing a model with utterance-level mini-batch with another model with dialogue-level mini-batch. Okay, so you're comparing two models. One of them was mini-batched utterance level. The other one was mini-batched dialogue level. If you are working with them together, you should use bigger batch sizes because that's when they converge. Well, we acknowledge the fact that most of the glove embedding-based models tend to be small, and using a larger batch size in these models for utterance-level mini-batch construction is not a problem. We think it could be a colossal issue in contextualized word embedding-based models such as BERT. So this is a transformer model. So they're saying... Oh, right. So a larger batch size means you have to wait longer for each training step. So if you have a lot of weights to update, as you add more and more data for each training step, your training time is going to get, much, much bigger. And I think that's just what they're going to say here. Models like BERT have billions of parameters and use large batch sizes to train these models. And using large batch sizes to train these models can be one of their bottlenecks. In such scenarios, we recommend using dialogue-level MiniBatch, which can still perform decently with relatively smaller batch sizes, as can be seen in Figure 11, and be computationally inexpensive compared to utterance-level MiniBatch. Okay. The experiments conducted in Section 6 are based on utterance-based MiniBatch training, so they just use it in the future as well. Okay.
I remember I was just going to say you also have like an NLP for developers on board, which is really great because you kind of talk a little bit also about that specifically.
Yeah. It's a chonker. It's big.
Yeah.
Although much smaller than GPT-3. So, or I think GPT-2 is bigger than BERT as well. More T. But there's been like a drastic increase in the size of state-of-the-art NLP models. Certainly while I've been in the field.
Are they just kind of growing in size, would you say? Yeah.
Yeah. Which, sort of the general pattern in machine learning in general, but it does have, like, it's much more expensive. I want to say, I could get getting this wrong off the top of my head, but it costs like $2 million to train GPT-3 just in compute time. Wow. And also there's a pretty big environmental cost as well for machine learning models. It's
interesting.
Is it worth it?
Yeah, I have to weigh it up. Depends what you're really intending to ask it, I guess, and what you're really going to get out of it and everything. So you have to weigh up your reasoning.
Yeah. Let's check the next section that Soujanya talked about. 616364. All right, so let's go down to 6.1. Classification in shuffled context. Oh, interesting. So this is, I think we talked about before we started the reading group, we talked about perturbations. So that's where you just like mess things up and see what your model does. So this is one of the ways that they've messed things up. You want to take this section?
Yeah, totally.
While I drink tea?
Yeah, sure. Always in favor of drinking tea. To analyze the importance of context, we shuffle the utterance order of a dialogue and try to classify the correct label from the shuffled utterance sequence. For example, a dialogue having utterance sequence of U1, U2, U3, U4, and U5 is shuffled to U5, U1, U4, U2, U3. This shuffling is carried out randomly, resulting in an utterance sequence whose order is different from the original sequence. We designed 3 such shuffling experiments. In one, dialogues in train and validation sets are shuffled. Dialogues in test sets are kept unchanged. In the second, dialogues in train and validation sets are kept unchanged, whereas dialogues in test set are shuffled. And in 3, dialogues in train, validation, and test sets are all shuffled.
So people sometimes mean different things by train and validation, test and validation. But the basic idea is machine learning methods learn, well, I don't want to say they learn patterns, but they approximate patterns in data that they've seen. So you want to make sure that your model also works on data it hasn't seen. And usually people do like a test train split or train test split. So you have your training data, and then once your model's done, you run it on your testing data. And sometimes there'll be a third set that is completely held out and you never see until the very end when you're comparing your models. I would usually call that validation data, but here it sounds like that's being called test data, which is like the different data is being called. Do you want to take the next section?
Yeah, we analyzed the shuffling strategies in the Glove BCL-STM model. In theory, the recurrent nature of the BCL-STM model allows it to be capable of modeling contextual information from the very beginning of the utterance sequence to the very end. However, when classifying an utterance, the most crucial contextual information comes from the neighboring utterance. In an all-altered utterance context, the model would find it difficult to predict the correct labels because the original neighboring utterances may not be in immediate context after shuffling. This kind of perturbation would make the context modeling less efficient, and the performance is likely to drop compared to their non-shuffled context counterparts. This is empirically shown in Table 5 and Table 6. We observe that whenever there is some shuffling in train, validation, or test set, the performance decreases a few points in both the datasets across all of the tasks and all the evaluation metrics. And notably, the performance drop is highest when the dialogues in train and validation sets are kept unchanged and dialogues in test set are shuffled.
So they're saying that the shuffling hurts, which makes sense, right? Like, if we took our discussion here and like randomly shuffled when I say something and when you say something, it would be pretty hard to follow for me as a human. And they're saying that these models are also having a little bit of a hard time following it. Table 5, here we go.
Is that because it's kind of turn-based? Or is that because it's kind of turn-based and it's kind of needing that? Or
yeah. So I think the two things that are important here is, one, that the underlying data does have a structured order, right? Language has an order to it.
Right.
And you could probably get the same results if you were just like taking paragraphs of a book, because there's this understanding that you're going to read through those paragraphs in order. It probably wouldn't have the same effect if you were like looking at a collection of haikus where they were in like, I don't know, chronological order or something, and there's not like a dependency between the texts, and knowing about one haiku doesn't help you know about the second haiku. That's just an example. And the other thing that I think has an effect here is that LSTMs are a recurrent neural network. It's a type. Recurrent neural networks weight things closer to the current thing that they're looking at a little bit higher. So they care about distance much more than, for example, transformer models do. Transformer models don't care about distance as much because they're paying attention to the entire input, phrase, sequence, utterance, haiku, whatever it is that they're looking at. They pay attention to the whole thing. So my guess would be if you did the same experiment with a transformer-based model, you might not see quite as big of a drop. But I don't think it's bad that we see a drop here, right? Because that's not human-like, right? If you were building a Rasa bot and you just like shuffled the turns of your stories and were like, use it.
Yeah, I guess it's
would be
proof that it
awful.
doesn't work the right way in a way, like that it's not working in this way. Yeah, it's more human. Okay. So bots table.
Yeah, basically, once you add shuffle, number go down, and it goes down the most when, so the test set is the one that they're using to generate these numbers, and when only the test set is shuffled, that's when the numbers go down the most. So here, the model is learning about the patterns in language and conversation, and then the validation set's like, yep, good to go, and then the test set is just like off the rails, and then the model does worse. Yeah, and pretty reliably. Yeah, so this could be, I don't think this is like explicitly cognitive modeling. Like, I don't think they're explicitly trying to be human-like, but I think that it does have that flavor to it, you know? And this is same thing, same pattern, much stronger though. I feel like this is, for a lot of these tasks, like 5 percentage points is a really big change. They're not really percentages, but a 5-point change in F1 is a very large change. So a 20-point drop is pretty significant.
Oof. Yeah, in comparison to the top, I mean.
Okay, sorry, that's not you. Wake up.
Early morning. I'm looking at looking at diagrams and graphs and stuff in the early morning. Stuff. We'll keep it going.
All right, that was section 1. The next section that Soujanya suggested was section 6.3. Scroll. Controlled context dropping. You want to read this bit as well?
Sure. Controlled context dropping. In Table 3 and Table 4, we observe a large improvement in performance in the contextual models, so BC, LSTM, and LRNN, compared to the non-contextual CNN models. Now, we intend to analyze why this improved performance is observed and how recurrent models such as BCL-STM uses contextual dialogue information from past and future utterances effectively. To understand this effect, we make a comprehensive analysis of the GLOVE and BCL-STM model and design an experimental study with controlled context dropping. In the default setting of BCL-STM, the full dialogue history and future is available to the model. Now, through a number of different experimental settings, we vary and limit the contextual information that is available to the model and study how the results are affected by it. And please refer to the figure 12 for a visual representation of the controlled context dropping method.
Yeah. So, CNNs, I haven't worked with a lot, but I think they're similar to transformers in that you can use information further away from your referent point without a penalty. And then I think we mentioned this, the B in bidirectional stands for I'm looking left and right in terms of text. Let's see figure 12. Let's click on the hyperlink for figure 12. All right.
There we go.
All right, so we're doing some futzing. Here's our dialogue. So we are taking away the most recent 3 turns. We're taking away the 3 turns before the most recent 3 terms, and then future, and then far future, using that same sort of pattern. So you get rid of information.
It's removed and then tested.
And I don't think we need to read the method section because I think that cleared it up for me. And then observations. We report the results for controlled context dropping experiments in table 7. We observe that long distance context is much more important for emotion classification in IEMOCAP, however that's said, compared to the rest of the tasks. Row 48 in Table 7 refers to the experimental setting where full conversational context is used during training, but only 5 contextual utterances from the past and future is used in the test set during evaluation. In this setting, the performance drop in IEMOCAP emotion classification is significantly higher than the other tasks, indicating the importance of long-distance contextual utterances. Wow, I could have used some gray shading here to see which numbers were bigger.
Yeah. Did you say row 37 or something was the interesting one?
That sounds right.
Yeah.
Okay, so this is... Okay, so each of these columns is a different data set, and it's also... There's 2 different measures as well. And then here's what they did. So they take away
different sections.
All the past, all the future. Yeah, so I would guess that this number would be pretty high across the board, where all the future is not available during training and testing. Or at least it won't go down significantly. Okay, so it's because humans don't have access to the future when we're using language most of the time.
Interesting. So I thought future would be like predictions though, or is it just kind of actual kind of what's to come in the actual dialogue?
Yeah, they have the actual
right.
actual text. So if we were looking at like the word for here, we would know that more important were before it, but we'd also know emotion classification was after it.
Right.
Where were we? Sorry.
So
I'm struggling today.
We were on the, what was it? It might have hyperlinked you upwards. Oh, there it is. Yeah, that's the one where we finished.
Table 7, long distance context is much more important for emotion classification. Row 48. Oh, here we go. The full conversational context is used in the training and then not in the, I think actually it's row 47, looking at it. Right, because row 48 is that
it
the
says,
full train.
Sorry. Yeah.
Go ahead.
No, I was just going to say it says a reduction in performance is most significant in row 47. That's what it says, I think. On the right side there.
Oh, over here.
Yeah.
There we go. Dropping all the future utterances further worsens the results in all the tasks. The reduction in performance is most significant in IE mocap. We also observe some interesting results for the setting of training on full context and evaluating by removing all the past context. So training gets everything. And then we remove the past when we test, which would be this one, which is also pretty low. For daily dialogue, emotion, and act classification, there's significant difference in performance in these two kinds of context control settings. Completely removing the past context results in much poorer performance, signifying the importance of contextual information flow from past utterances in daily dialogue. Okay, I'm just sort of skimming this next bit. So for the persuasion data set, a small window tends to work. We also observe that the BCL-SCM works better than the Glove CNN model on all the data apart from the persuasion from good, which makes sense because it looks like the persuasion for good cares the least about context based on their discussion here. In any conversational classification setup, past contextual information is elemental for recurrent models to understand the flow of the dialogue. I think that is a good thing to know. And also, you know, fits with certainly my intuitions as a human dialoguer.
Does it mean like crucial? It's crucial for recurrent model?
Oh. Yeah, I don't know if there's like a mathematical definition for element here, but yeah, it's important.
Okay.
Additionally, from the results in Table 7, we can also conclude that future utterances provide contextual information for the various classification tasks. I mean, it makes more sense that you're going to be able to do better figuring out what's going on now if you also know the future. I don't know how useful that is for, like, you know, applications.
Yeah, real applications.
Although I guess, does the model that they talked about here have like input as a prediction of what the person's going to do next? Sure don't. So I'm wondering if this is maybe because I think when you are having a conversation, there is, just like on the human side, an element of predicting how your interlocutor is going to react, right?
Yeah.
And I guess that here is represented by like the past utterance, I guess. But this person doesn't have, so person X, it looks like in this model, doesn't have a model of person Y's internal state. And for especially a lot of the natural language generation research that's been going on, it's pretty common for an agent that's generating language to have an explicit model of what their interlocutor's knowledge and beliefs are. Like there's like a, there's like a table where it's like, they know the ball is blue or whatever.
Yeah. It's like a very clear, whereas I guess sometimes in conversation, in human conversation, you don't always know.
Definitely.
But it's very like, it's just a, like you said, text table, I guess, where all the information's there to refer to.
Where are we on this section? Okay, there we go. Yeah. If the BCLSTM, oh, go ahead.
Oh, but I'm just gonna carry on for you, but
oh yes, please. Actually, one sec. Let me see if Soujanya suggested section 6.4 as well. So if you just wanna keep going from here.
Sure, from 6.4. Yeah. So yes, speaker specific context control. That's what we are. Yeah. The further evaluates to further evaluate the intra and inter-speaker dependence and relation across the different tasks, we adopted two different settings as follows. So WO inter, which is when classifying a target utterance from speaker A, we drop the utterance of the speaker B from the context and vice versa. And then I guess without intra, when classifying a target utterance from speaker A, we only keep utterance of the speaker B and drop all other utterances from speaker A from the context and vice versa.
Yeah. So inter is, and this is more for audience members who might not have run into these terms. Inter means within, between, and intra means within. I remember, because in the US we have an interstate highway system, which means it goes between states. And every state also has like an intra-state highway system, but nobody calls it that, which is just like highways that are only within the state.
Good way to remember.
I mean,
I'll have to learn the US thing and then I will learn. But it definitely does help actually. Like thinking interstate, I'll think interstate and then I'll learn that. Yeah, and so these two different settings are visually illustrated also in section 6.4.
Is it? Yeah, okay, this one. Okay, so this is blue circles are this person. So in this model, you remove everything the other person said without inter, and without intra, you remove everything they said. Why though?
Yeah, just why though?
I think this is more like, what can the models handle? Just gonna mute myself for a second. Somebody's feeling barky.
Well, me doggy. So I guess we'll continue. So utterances of the non-target speaker are important. Involved. The first setting course is LSTM to only rely on the target speaker of the target utterance. Context in prediction. The results are reported in table 8 and 9. As expected, performance drops are observed for all the datasets, but IMO-cap and daily dialogue for emotion recognition reinforces the fact that contextual utterances from the non-target speakers are important. Performance drop in daily dialogue dataset for act classification is noticeably the steepest. To understand the behavior on the IMO-cap dataset, we need to refer to the figure 8 and 9. In figure 9, all the diagonal cells have high intensity, thereby indicating a pattern of the speakers maintaining the same emotion along a dialogue. On the other hand, figure 8 illustrates inter-speaker label transitions that maintain emotion consistency. Emotion of a speaker is reciprocated by the same or another emotion of the same sentiment by the non-target speaker. Notably, figure 9 shows distinctively higher density in its diagonal cells as compared to the diagonal cells in figure 8. This suggests that the speakers in the IMO-cap dataset repeat the same emotion along consecutive utterances. This tendency of the IMO-cap dataset, as shown in figure 9, overwhelms the inter-speaker patterns depicted in figure 8. Consequently, this induces a data set bias. Hence, removing other interlocutors utterances and from the context makes it easier and less confusing for the BC-LSTM models to learn relevant contextual representation for the prediction.
Okay. So they're saying that the only place, let's see if I can, we're on page 20 now. The only, oh, I think they meant figure 8, not table 8.
Yeah, I think.
There we go. So this one. So they're saying that for these two tasks, you can remove the other person's emotions because they're very easy to predict. It's either going to be almost always the same as what the person you're looking at is feeling, or it'll be no emotion. Like, this is a pretty easy task. You can always just guess no emotion. You can always guess no emotion, and it'll be usually right. Yeah. Marco says, hi, Rachel and Emma. Hi, Marco.
Hi. Welcome.
Whereas for these transitions, it's much more difficult. So this is between speakers, and this is within speakers. So the same speaker is a little bit less consistent, actually. There's a little bit less difference about, excuse me, difference about the dialogue.
I have to run up really quick.
So I'm going to keep going. Emma has, she let me know about this, a personal thing going on. All right. That makes sense. Pop that over. Marco says, is the paper Utterance-level dialogue understanding an empirical study? Sure is. Scroll. So we were in section 6.4, I think. Here, okay. So what if you remove the history of what the person who's speaking now said? What happens? That's the question we're gonna answer now. I'm sorry, y'all, I'm so tired. In blah, 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 it's important if you remove it, particularly from the daily dialogue and multi-WAS data sets.
Hey, sorry, I'm back. Someone at the door.
I'll bring you back onto the stream. So we're moving on to the intra speaker. And here, if you remove the utterances from the same speaker, you still lose information, right? The history of what somebody said seems to be important. In these tasks, dropping the utterances of the non-target speaker results in more performance degradation as compared to the case when utterances from the target speaker are removed from the target utterances context. Okay, so getting rid of what the other person said is more disruptive than getting rid of previous things that the current speaker said. This observation also supports the dialogue generation work, Show et al. 2017, that mainly considers previous utterances of the non-target speaker as the context for response generation. For emotion classification in daily dialogue and strategy classification and persuasion for good, the results obtained from without intra setting are also relatively lesser compared to the baseline BCLSTM setting. So it goes down. And for emotion, it looks like what you were feeling previously is more important than for figuring out what persuasive strategy you're going to use. In that case, what the other person said is more important.
And that gives you an indication, like what the person said before, how it's going to go. My screen just went black. That's back now. So just my whole screen just disappeared. That's interesting. Sorry, I just kind of jumped back into it, but caught at the end.
Oh, we didn't get very far. I think I scrolled a bunch and said I was tired. Yeah, interesting. I'm gonna see the next section. 6.5, he recommended skipping. 6.6, 6.7, 6.9, and 6.11. And I'm just going to look at the title of those really quickly. So a text with context and target paraphrasing. So this is trying to make it harder for the model by saying things in a different way. And then 6.7 is, that's a long one, label constrained dialogue level utterance augmentation. I'm sorry.
That's a long one.
This sounds outside. Yeah. Labels of consecutive utterances are often interrelated. Recurrent models usually learn this pattern. Blah, 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 blah. Okay, so this is, well, utterance augmentation. So they're either adding information or they're adding text. Concatenates the end of the original utterance. Okay, so here they're squishing stuff together and then seeing what happens. And then 6.9, performance for label shift. So label copying can be useful for figuring out things like emotion, act, or intent. What happens when there's a change of label? Are they sensitive to that? And so we only probably have time for one more section, which is why I'm going through and looking at the different
very helpful of the research as well, to give you a little suggestion on what we should go through, because we were not sure last time we should go through all of it. It's quite a long one, isn't it? 37
rich paper. Yeah. Hefty, I would say.
Hefty, yeah.
And then sequence tagging using conditional random fields, CRF. So this section 6.11 is the newest section. I think section 6.6 sounded the most interesting to me, but Emma, of course, you also get a vote. And that was the one where you rephrase things to see if you can get the model.
So it's between this one and what's the other one, sorry? Rephrasing it?
All of the rest of the ones that we looked at. So the last one, which is on conditional random fields and sequence labeling, the one where you sort of squish utterances together and see what happens, the ones where you randomly change labels and see what happens. And the reason I think this one might be particularly relevant to Rasa folks is because the research team has been working on some paraphrase related stuff. So I thought it might be interesting.
Yeah, totally. Let's dive in. I think it makes sense to definitely go for the stuff with the rest of the interesting. It's useful.
Okay. Do you want to read this first section?
Yeah. So yeah, a text with context and target paraphrasing. So modern machine learning systems are often susceptible to attacks that slightly perturb the input without any drastic change in the semantics. Although prevalent in images, adversarial, oh my god, sorry, my screen just went black again. Sorry guys, this keeps happening.
Worries.
Where am I? Yeah, so adversarial examples also exist in neural network-based NLP applications. In the context of NLP, crafting adversarial examples would require making character, word, or sentence level modifications to the input text to trick the classifier into misclassification. Paraphrasing sentences is one such method to construct effective adversarial examples. So it's Ear et al. 2018. We conduct several experiments to evaluate the sensitivity of utterance-level dialogue understanding systems to input paraphrasing. It should be noted that although task-specific adversarial strategies could be adopted, we chose to use a general set of attacking strategies in order to understand the behavior of the baseline across different tasks and data sets. Okay. And this one,
sorry.
It's okay.
Let's see if I can get both there. In there.
I think we got there, yeah.
So they're saying that they're using paraphrasing across all of the different tasks that they're doing to see if they can trick their model. It also facilitates a fair comparison among the tasks and whether there is a confounding factor that differentiates one task from another under the same attacking strategies. Let me zoom like way in so we can actually read these. All right. So here, originally it said, John, I was looking through some magazines for idea about where we might go on vacation this year. Ha! And it's been paraphrased to, John, I'm searching for some ideas where I could go on vacation this year. Neutral. And then John replies, I already told my buddy Mark that I'm going hunting with him in Alaska. And then the original is, you can't be serious. And then the rephrase is, you better be serious. Serious. Which I don't know that this is angry.
Yeah, when you switch it, it's different.
Yeah. Okay, so they're saying that this was originally neutral? Oh, I see here.
Yeah.
So they're trying to get the label for this one to be angry by changing this label to angry, I guess? Or this was angry all along? I don't... Let's see.
Oh, wait,
predictions under modified context.
Did they change the site? Oh, I've already... Oh no, they didn't even change this one. That makes no sense.
Yeah. I would say that, for me, this no longer looks like angry. It was like, oh, you better be serious. It's like, I hope you're not kidding, because I want to do that, would be my interpretation of that just from text.
Yeah.
Let's see. We use the following scheme to analyze this effect. The input utterances are modified at either word or character level. For word level modification, an average of 3 to 4 words are selected per utterance and masked. The pre-trained Roberta model is then used to fill these masks with the most likely candidates. So this is just a language model that guesses what's going to be in the empty spaces.
That space, yeah. I remember you were talking about masked transformers.
It is, in fact, a mass transformer.
Yeah.
The utterance
no people devs, guys.
The utterance with substituted words form the new input. We call this method paraphrasing-based attack. The character level modification is achieved by changing the spelling of, on average, 3 to 4 words per input utterance. We call this method spelling-based attack. Sorry. Okay.
It's attack.
So this is like introducing typos and seeing what happens. You want to take the next section?
Yeah. So for each utterance, UT in the dialogue, we take a window of W, immediate neighboring utterances, so in brackets context, on which the above modifications are performed. The window is selected as follows. Only past W utterances. So, sorry, what's W representing? Do you know?
I think it's just a number.
Just number, okay.
It's like the past 5, the past 3.
I see. So yeah, only past W utterances. So UT and W comma or break. UT and then 1.
Yeah, so it's -1. So
-1.
just lowercase t almost always means time. It's like a point in time.
Oh, okay. Thanks.
They don't say that in the paper. You just have to know it.
So only future W utterances as soon as UT, so time plus. Oh, sorry. Is this an I? It's just a bit hard to see on the screen.
Okay. So they're saying that we're going backwards W points in time, changing all of those. We're going forward W points in time, changing all of those. So T plus 1 means the utterance or word after our current one.
Oh, okay. Yeah, and then UT plus W. And then past W and future W utterances is UT minus W, and UT minus 1, and then UT plus 1, and UT plus W.
And then the dot comma here means, and also all the things in the middle.
So, oh yeah, so it's like everything that's going on between, and these are like kind of the most significant parts, yeah.
Ow.
And then, you're right.
Yeah, I just like hit my desk.
Past W, future W, and target utterance. UT minus W, and then in between UT minus 1, UT, UT plus 1, and then space UT plus W. And the only the target utterance is UT. These are all the different windows, I guess, selected. In the last case, the window is empty. In other cases, we experiment with window size W equals 3, 5, and 10.
Okay. So changing fewer or more words, turns, stuff. We train an utterance-based glove BCLSTM and a glove CNN, just the same two models they've been using the entire time. So they start with ones that are trained on just like the baseline data, and then they, during evaluation, they add these changes. So like an adversarial attack, given that a lot of training data is scraped from the internet, you could actually see an adversarial attack in your training data, which is just something to know. But it's more often that you'll see adversarial attacks during, like, when your model is being served and people are using it. So that's probably why they've picked this particular way of doing it. And then the results are down here. So let's take a look at the results and then call it a day. Let's see, table 11. There we go, table 11. Okay. So here is, this one is the paraphrasing, the PA. The essay is the spelling. This is whether the past has been changed, the future has been changed, the target has been changed, and then the wideness of those changes. And to start out with, these are what the models were originally, and then this is how they do after these perturbations. And what I am noticing is that all of the models do worse once you start to add these perturbations. So they're not, robust to this type of attack. It does hurt their performance, except for persuasion in one instance, and that is when the past 3 utterances have been messed with a little bit. And then the biggest changes is, it looks like when you change all of the context, so you're paraphrasing all of the context, or you introduce spelling errors. And it looks like, just from eyeballing it, this is where you see the biggest drop for the persuasion ones. For IEMOCAP, the spelling errors are worse. For daily dialogue, the spelling errors are worse. For the emotion, for speech act, the paraphrases are worse for daily dialogue. For intent, paraphrases are worse. For persuasion ER, paraphrases are worse, and for persuasion EE, spelling attacks are worse. So I think the most relevant thing for a Rasa developer here is this intent is not very robust to paraphrasing. So by including a wider variety of rephrasings in your training data, you might be able to help maintain high system performance even when things are said in different ways, would be my general thing. Halunu, this says, great stream, been listening and found it very interesting. Thanks. Happy to hear that. That's what I get from that. This is a chunky table. There's a lot going on here.
Kind of like try to also like comprehend here, like the because you said like PAs, the paraphrasing essays, like the error, spelling
Yeah.
error. Yeah.
So they're just like randomly changing characters in a word. So like cat might become cag, C-H-E or something. And then this one.
The more examples, the better, you mean, as well.
Yes, definitely.
That makes sense. That's what we always, the more real examples, the better as well.
Yes,
yeah.
definitely.
Yeah.
Definitely. But it's nice to have like a paper to point to, you know?
Definitely.
So looks like here, okay, so it also looks like the glove model is more susceptible. So this CNN is more susceptible to these attacks than the BCLSTM, which is interesting because based on this, I would expect transformers to maybe also be more susceptible to these attacks than RNNs. Oh, and here's an example of the spelling correction. So it said, John, I was looking, same thing. June is looking through some magazine for ideas about where we might go on vacation this year. And already told Mew Beauty Mark that I'm going hunting with him in Alaska. You can't be serious. So here, it was originally angry, and now it is surprised, presumably because John is having a stroke.
Oh God.
I don't think he's having a stroke.
No.
It's just
yeah, it's kind of what's happening there. I mean, you could imagine, but yeah. Oh my gosh, that's. I always find those quite interesting, actually, seeing like the real examples. How this works.
Yeah, but also, I am noticing just looking at it that these don't look like very natural-looking typos. So typos tend to follow a couple of patterns. So one is that characters near each other are switched, characters are deleted, characters are doubled, and it doesn't really happen randomly. And these look like they are a little bit random. Like, how likely would you be to misspell MY MEU?
Yeah, when
I'd say I'd be more likely to misspell it.
Yeah.
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 You're gonna reach. Cool.
It's quite a reach, yeah. Unless maybe the body
sorry, middle finger.
No, and looking at the keyboard that doesn't make any sense. Yeah. So if it's okay, interesting. Yeah.
So I might expect also looking at these, sorry, I know I'm bouncing all the way around. It looks like the glove can handle paraphrasing. Like these are switched, right? For this one, the paraphrasing is better than the spelling. Paraphrasing, nope, spelling is worse, spelling is worse. Spelling is like a little bit worse. Paraphrasing, okay, so what works on each class of model and each data set looks to be like a little bit, different.
Yeah.
Interesting.
And the vectorizer, I mean, that's both is a vectorizer, so it means it's just kind of like pretty clear what's coming next. It's like a quite fixed way of working. Is that what you would expect then, like the results there?
Yeah, this is a good question. So I would expect in general spelling attacks to be harder of this kind because it's going to take things and make them out of vocabulary, right? Like I don't think these models have seen the word MEU before because that's not really, it's maybe an acronym, but it's not like a common English word like MY, my. So in general, I would expect that these spelling attacks take text that was recognizable and make it less recognizable by these systems, and that paraphrasing attacks should be a little bit more doable if the paraphrases are of high quality. So they're saying for classification tasks, spelling based is much better, and that the more spelling mistakes are introduced, the worse it is, which I think makes sense. Spelling changes create out of vocabulary words that are missing from pre-trained glove. So these models are, you're like, here's all the words and what they co-occur with. And if you have a word that hasn't been shown, it's not going to be able to be turned into numbers easily. That makes sense?
Yeah.
And And then these, oh, interesting. So only what is this person doing? Only the ones that affect the past utterances change. If it affects future utterances, nothing changes, which is interesting. And then they're just sort of talking about the different changes. Interesting. So, yeah, I think that see, okay, so they do talk about BERT a little bit. So transformer-based models. In principle, our findings in Table 12 can be related to how transformer-based tree-trained language models work. For example, in BERT, the masked language modeling, MLN, and next sentence prediction, NSP, objective, forces the model to infer or predict the target using contextual information. Such contextual models are more powerful and robust because context information plays a crucial role in almost every natural language processing task. An objective similar to next sentence prediction in BERT or permutation language modeling in XLNet can be used, for conversation level pre-training to improve several downstream conversational tasks. Such approaches have been found to be useful in the past. In XLNet, the language modeling is done by shuffling all the words. So instead of having one model point forward, one model point back, or one model is paying attention to everything, you only look at the past, but you shuffle things so that the past sometimes includes the future as well. Is the general idea of that paper. Interesting. So the more context you have, the less perturbation throws you for a loop. So I would expect maybe like a policy like TED. Well, TED's a policy. I guess we'd have to use an intent classifier. So I'd expect something like diet to maybe be a little bit more robust because it has that long distance dependency. Anyway,
yeah, what the hell that would do here? I'm curious.
Yeah, that's a good question. Because it's not really in either of these families of models. It's closer to BERT.
Yeah.
Yeah, that could be a good question for the research team, or Diet's open source. So if one of our community members wanted to maybe write a blog post about that, it'd be an interesting community contribution.
It would be interesting. And then you would enter into the contributor program, guys. Get swag.
Yeah.
Get the cool swag.
All right.
Yeah.
I am out of focus. I need to take a coffee and a nap. Wow, there was so much going on in this paper.
Yeah, it's
how can
a lot of work.
A lot of work. I would say that this is like several papers. Very, very rich.
And so I would say it's a bit hard to also bring it all together, really. Like, it has kind of like more summaries of on each level rather than like an overall. Yeah.
I think if I could pick like one overarching theme from everything that's going on in here, it would be the context is important, right? And that context includes more than just the words. It includes like emotional context is going to be very stable over time in a conversation, whereas like persuasive strategies are going to be much more varied over time. And when you're training, if you are training using little chunks of context, you're going to get better results faster than if you're just sort of randomly sampling utterances. Yeah, so I would say I know the paper's called Utterance-level Dialogue Understanding, and I would say that the main results are, if you want to do well with utterances, you need to be modeling the larger dialogue, and also what you are modeling within the dialogue is going to affect what methods you should use and how robust they will be, and other stuff that we didn't read. I think that's my
it's fascinating, super fascinating actually. Like also learning things are really interesting things about how conversation can be, well, how it's influenced as well, and how you can even see that as well when you're actually running these models and seeing how it plays out. That it kind of does reflect how it can happen in real life as well. Like, it can escalate or people are angry or so I think it was like sad emotion and like excited and things like that were the most to, or at least on some of the models were to be repeated. And I found that really interesting. I've never really thought about before.
Yeah, definitely a lot to learn from this paper. It is on archive if anyone would like to read the whole thing. And I believe they just also did an update as well. So you can see October 19th. It is work in progress. All right.
Awesome.
Coffee nap.
Yeah. You got some coffee.
Thanks for joining me, Emma.
Yeah.
I will be back tomorrow with live coding. We'll be hopefully finishing up the 2.0 migration on the chatbot. Dialogue quiz, of course it's a chatbot.
Oh, that's awesome.
And Vincent's season 3 of the chatbot, what's it called? Breakout Bot Diaries continues, and he is it's actually like a game development series because it's a text-based adventure game. So those will be coming out every day this week. I think episode 3 came out today, and the newest podcast episode launched yesterday on YouTube, and also hopefully most of the places you can find podcasts. And I think that's all for this week.
Loads of content. Lots to keep you going.
Yes, lots.
There's a lot to keep you going. That's great. That's yeah, love this stuff. And yeah, thanks a lot for having me on as well. It's really enjoyable. Learned a lot of things. So it's really nice.
It's lovely to have you. And if y'all make some code contributions or support contributions, Emma's going to be the one who hooks you up with cool swag.
Yeah,
as a thank you.
Definitely. Make sure you're usually we're checking out lots of things that are going on, and there's always lots of very amazing contributions that come through. But yeah, you can always, if you want to get in touch with us, either on the forum or just community@rasa.com email. So let us know what you're up to.
Yeah, we'd love to hear more.
Yeah.
All right. Thanks so much for joining us today. Thanks for joining me, Emma. Emma, your name is Emma. I'm gonna take it out.